Okay, so here's a quick video for section 8.2. We're going to talk today about a new thing called the geometric distribution. And let me remind you that if you see something like this, the probability that x is less than 3, where x is some random variable, it really matters what kind of random variable x is. If x is a normal random variable, you use normal CDF. If x is a binomial random variable, you might use the formulas we did in section 8.1, or you might use binomial CDF. Let's say that x is some discrete random variable. You have a little chart like this. Well, then you would just kind of figure it out. Let's say x is some continuous random variable like this. You might use some geometry to figure it out. So it really matters what x is, how you do a problem just like this. Well, today we're going to add one more thing to the mix. What if x is a new kind of random variable called a geometric random variable? So let's talk about, first of all, what a geometric variable is. Sort of, it's going to be like a binomial random variable. The good news is it's a lot simpler and there's a lot kind of less to talk about. So like we had a checklist for a binomial random variable, now we have another checklist for a geometric random variable. And the good news is it's almost exactly the same thing. 1, 3, and 4 are exactly as they were for binomial random variables. The only really difference is right here. No longer do you have a fixed number of trials. The difference between a geometric and a binomial random variable is that what you're interested in now is the number of outcomes until you get the first success. So going back to my free throw analogy, now it's not going to be you're going to shoot 10 free throws every time. You're going to keep shooting until you make one, and then you're going to stop. Or in my example of throwing darts, you're going to keep throwing a dart until you hit the bullseye. Or if there's a family who's having children, they're going to keep having children until they get a girl, for example. So something like that. It's not a fixed number of trials, you're going to keep doing something over and over again until you get a success. So here's just a quick example, a very typical problem. Now we're back to shooting free throws, only now you're a really bad free throw shooter. You only make 15% of all your free throws. And basically, what is the probability that you're going to keep shooting until you make one? And what is the probability that the first one you make is the 7th shot? Okay, so here's our notation, probability x equals 7. We care about the probability that x is which shot your first success occurs on. We want that to be the 7th one. Well, if you think about this for a second, it's actually, forget about any kind of formula. We could actually have done this problem back in the probability chapter. Because if your first one happens on the 7th one, your first success happens on the 7th one, what happened on the first 6 shots? Well, that means you must have had a failure. So the probability of success here is 0.15, so the probability of failure is 0.85. So what happened on your first 6 shots? Failure, because you failed to make one. So we do 0.85 to the 6th. And then what happened on your 7th shot? Success, you made it, so it's 0.15. So basically we just do failures to the, or Q, to the number of failures you want, and then one success, and it turns out that ends up being about 5.66%. Pretty straightforward, actually, and almost all the geometric ones are just this simple. So a bunch of failures and then a success. Well, it turns out, I know you guys like thinking about formulas, so let me actually give you the formula, and here it is. And it's exactly what I talked about on the previous page. Remember, it's the probability of x being some number of kth trial is q, which remember is the probability of failure, k minus 1. So if you want your first success to happen on the kth observation, you had k minus 1 failures and then 1 success. So it's q to the k minus 1 times p. Turns out on the calculator, it's not very hard, but you can do this on the calculator also. It's GeoMPDF. It's actually, I think it's GeoMetPDF. The P standing for probability, because we went over an equal sign there. And now we don't have an n anymore. So for binomial, it was npk. Now it's just pk. So we could have done this previous example just using a calculation like this. GeoMPDF 0.15, 7, and that would have given us the exact same answer we got in the previous one. Okay? a little bit of difficulty. What if now we want to say what's the probability that your first success happens within the first 7 shots? So either your first, second, third, fourth, fifth, sixth, or 7th shot. Well, now actually we rephrase this question as a less than or equal to. Okay? So if you think about it, if it's less than or equal to the 7th shot, it could have been the 7th, or the 6th, or ... all the way down to the 1st. And notice here I go down to the first one because you can't get it must take at least one shot. It can't happen on your 0th shot. Well, the only really way to do this one is to just say this is the 7th shot. That's the calculation I showed you on the previous slide. This would be the 6th shot. Look, now you have 5 failures, not 6. Your first success was the 6th shot. And this is a 0 up here. It happened on the first shot. And of course, anything to the 0 power is just 1, so this is going to just be 0.15. If you add those all up, yep, you get 0.67867, about 68% roughly. And on the calculator, you can do, there's a way to do it on the calculator. It's geom CDF. Remember, the difference between PDF and CDF for binomial works exactly the same way here. The C stands for cumulative. So if you do geom CDF 0.15, 7, it does exactly this calculation up here, and you'll get the exact same answer. So there's not much more to geometric variables, but there's one little thing I want to show you. So I've drawn here the beginnings of probability histogram. And so the same free throw example, you make 15% of your free throws. So what's the probability of you making the first one? Well, clearly the answer is 15%. What's the probability of making the second one? Well, think, how would you figure this out? Wouldn't it be 0.85 times 0.15? The probability that x is equal to 2 is going to be you miss one and you make the next one. Well, that's going to be, if this bar is 0.15 tall, and we're multiplying 0.15 times 0.85, this bar is going to be 85% of the other one, so maybe something sort of like this. Well, how about the probability that x is equal to 3? Well, that's just another 0.85, right? 0.85, 0.85, 0.15. And I don't know exactly what number that is, but I know it's 85% taller than this bar. So it's going to maybe be something like this. If you think about it, I can kind of keep going. Won't every bar be 85% of the height of the one before it? Because there's one more miss every single time. This brings up an important idea about what the distribution of a geometric variable will look like. Well, it will always be skewed which way? Right. Good. That's because each time there is one more miss. The tallest bar will always be the first one, and every bar gets shorter from then on because every probability gets less from then on. Okay? Important idea. Okay, just wrapping this up, I want to compare a little bit geometric variables and binomial variables. Remember, we had a formula for the mean of x for binomial variables, which was n times p, and standard deviation of x, which was square root of npq. We want to do a similar thing now for geometric variables, so mu of x. Now, what would that even mean? In the free throw example, it would mean on average how many free throws would it take until your first success. Well, let's just say that you make 1 out of every 7 shots, so p is 1/7. On average, how many shots would it take for you to make one? Well, the answer would be, on average, it would take you 7. Turns out the formula here is just 1 over p. If you think about it, my example before with 1/7, if p is 1/7 and you just flip the fraction, you end up with 7. I recognize it's a little bit confusing because look, now we have a formula for mu of x and a formula for mu of x. Why aren't they the same formula? Well, it really matters that if x is a geometric variable, you use this formula. If x is a binomial variable, you use this formula. Okay? But for a geometric variable, literally it's just 1 over p. So in my example before, for the free throw example, we would say it's just 1 over 0.15, whatever that works out to be. Turns out there is no formula for the standard deviation for geometric variables. Well, it turns out there is a formula, but it's beyond the scope of this class, not in the AP exam, so we're not going to worry about it. So really the only new formula you have to know right now is just this one, which is the mean of a geometric random variable. And that really wraps up section 8.2.